Coastal regions are complicated because that's where fresh groundwater, which is formed on land due to the infiltration of meteoric water, meets salty groundwater, which is formed under the sea. Fresh and salty water are completely miscible, and you can make any solution between them. This means that a rigorous solution to a groundwater flow equation has to take into account not only the movement of the water, but also the movement of mass, specifically salt, which can exchange between the two groundwater regions. This is really complicated, and the methods to solve it are beyond the reach of many hydrologists. Fortunately, because fresh and salt water have such different physical properties, especially their densities, it's often possible to get an approximate idea of what's going on by treating them as distinct fluids that don't mix. Because fresh water is less dense than salt water and is accumulated by recharge from the surface, it takes the form of a lens that floats on salty groundwater. This is best seen by looking at a cross-section of an island, as shown here. The lens is thickest in the middle of the island and tapers to nearly nothing on the edges. Also, as I'll explain shortly, the freshwater lens has a buoyancy that requires it to float very low in the salty water, producing a giant root that extends downward much farther than the upper part of the lens, the water table, extends above the sea surface. Coastal regions can be visualized as one side of the island. Far from the coast, the lens gets essentially infinitely thick and we don't have to worry about saltwater anymore. But near the lens, which means within a couple of miles or so in most areas, saltwater is close enough to the surface beneath the freshwater lens to be an issue. As mentioned previously, we often treat the fresh and salty groundwater as immiscible fluids, but that's not actually true, and there's always a zone where the water is brackish or semi-salty that separates the fresh and salty groundwater. The thickness of this mixing zone ranges from a few meters to a few thousands of meters. Although we're primarily interested in flow within the freshwater lens, there's also flow within the mixing zone and also flow within the salty groundwater zone. Salt water is drawn into the mixing zone at depth and rises along the interface. If you look carefully at the arrows in the salty groundwater, you can see that there's actually a small circulation system set up where salty groundwater enters into the ground offshore and then rises to the surface in the nearshore environment. Water in the freshwater lens also rises along the interface and discharges right at the coast or in the nearshore environment. The discharge of fresh or brackish water in the nearshore environment is called submarine groundwater discharge and can play an increasingly recognized role in the health of shallow marine ecosystems. The shape of the freshwater region is easily described mathematically if we assume the two fluids are immiscible and the interface is sharp. It's a matter of equating the pressure at the bottom, taking into account the different densities of fresh and salt water. The result is shown here. The height of the water above sea level, here termed h, is equal to the depth to the saltwater-freshwater interface, termed z, times a constant that depends on the densities of fresh and salt water. If we plug in typical values for these densities, we get a very simple equation. Z equals 40 times h. In other words, the freshwater-saltwater interface is 40 times deeper below sea level than the height of the water table is above sea level. This result is called the Geibin-Herzberg equation after the two hydrogeologists who first derived it. For example, suppose you're some distance from the coast at a location where the water table is 2.5 feet above sea level. Given a typical water table gradient, this would put you about half a mile inland. How thick is the freshwater lens at this location? Well, the depth to the freshwater-saltwater interface, z, is 40 times the water table elevation, or 100 feet, and the lens looks like this. Most people are surprised how deep the root of the freshwater lens is, partly because the Geibin-Herzberg relationship is always distorted in figures to make the water table elevation more visible. For example, compare this image. To get the total thickness of the freshwater lens, you just add the part below the water table 100 feet, to the part above the water table 2.5 feet. The Geibin-Herzberg relationship also explains why saltwater intrusion along coasts can be such a big problem. Wells that extract groundwater from the freshwater lens lower the water table, and for every foot the water table is lowered, the equilibrium position of the saltwater-freshwater interface below the ground has to rise 40 feet. This upside-down cone of depression is called upconing and can be a very severe problem in coastal regions.